Right. So this work on Supermetal is motivated by moiré materials, but it's now evolving into something quite different. Seems to take a life of its own. Now, in the first two lectures, I've described a lot about the magic bullet for topology and quantum geometry, and that magic bullet is direct point. So one can ask, is there some magic bullet for correlation systems? It appears that strong interaction and narrow band generally favor correlated phenomena, and in particular, the extreme limit of high density state occurs in the flat band system, and density state is a delta function. So this applies to, for example, quantum Hall systems, lambda levels in a strong magnetic field, and it's been proposed in twisted bilayer graphene by Alan MacDonald, and that really led to the beginning of all the recent experiments, okay? At least motivated all the recent experiments. If we look at actually the band structure of twisted bilayer graphene, the calculation has been refined again and again over time. And this is the most recent calculations from Carcerius group. And taking lattice relaxation into account, it has been realized that the structural relaxation is extremely important. And as you can see that at different twist angles, from 1.3 degree to 0.93 degrees, the band width is reducing very rapidly as a decreasing twist angle. And this is a plot of the density states. And you can see that the by Hove singularity in the lowest conduction band and in the lowest valence bands are really approaching each other. And around this magic angle, they are almost overlapping. So this is the calculation, the best first principles calculation that we have so far, probably. Now, on the other hand, if we look at experiments, this is the STM experiment from Ali Yazdani's group. This is measurement of the tunneling density of state. And indeed, you see the two pronounced Hove singularities, but the energy separation are a few tens of millielectron volt. This is another measurement, not tunneling density of state, but compressibility by the capacitance measurement from MIT, Ray Ashuri and Pablo's group. And this measurement was done actually on exactly the same device that shows superconductivity and correlated insulator that's published in the original Nature paper. And again, you see that this compressibility measures dN d mu, which in the non-interacting limit would also correspond to density of state. But the dN d mu generally is a thermodynamic quantity as a function of chemical potential. And you also see these peaks, the Hove singularities. But again, when you see that the energy separation of these Van Hove peaks in the conduction and valence bands around 35 millielectron volt. So the authors noted this and made a comment that this mini bandwidth is much wider than most theoretical estimates. So I think people are still trying to sort out what exactly the bandwidth is in this twisted bilayer graphene near the magic angle. And in the limit of a complete flat band, one would expect quantum Hall type of physics might be extremely relevant. On the other hand, if the bandwidth is important, perhaps some kind of a Hubbard physics, like in high temperature superconductors, might be more relevant. So this is, I think, at the center of this issue. Is the system more quantum Hall-like? Is the system more Hubbard-like? So one thing that we played around a little bit, and this really worked by Bijan, Pablo fellow at MIT. So we noted from this STM measurements in various groups that the moiré superlattice is not exactly does not exactly have the triangular symmetry. Instead, it's a distorted triangle lattice. Right? So these bright spots are the AA stacking regions, and this amount of distortion has been quantified in this experiment, for example, from the Columbia group. And the authors attribute this distortion due to the presence of strain that is slightly different on the two layers of the graphene sheets. Okay, so this is known as a heterostrain. So, so we took this experimental observation as input and then calculate the moiré band structure using the simplest continuum model, but now taking into account of the presence of the heterostrain. And this is the band structure. And now you see that the moiré band width is much enhanced. Right? The Van Hove peaks are now separated by a few tens of millielectron volt. That is at least qualitatively agreement with the STM experiment. Moreover, we can look at the moiré band width as a function of twist angle for different amount of heterostrain. Right? And notice that the amount of strain we are using here are very small. So the smallest one is maybe only 0.1%. Now, without any strain, without any heterostrain, what happens is that the bandwidth would decrease to 0 at the magic angle and then become finite again. So there's this non-monotonous behavior of the reduction of the bandwidth that really defines the magic angle in the very early days of this field. But now you see that when a small amount of strain is introduced, the bandwidth seems to reach a plateau. Right? It doesn't have this non-monotonic behavior anymore. So this is also agrees with other STM measurement as a function of the twist angle. So it appears that how flat this band is, it depends a lot on small perturbations. So if one can remove the strain, the bands it may be possible to make the bands more flat. While in some of the current devices, the bandwidth may not be as small as we initially thought. So this brings me to this other regimes that even we don't have a completely flat band, even when the bandwidths are finite and important, we can enhance correlation effects by increasing the density of state around the Fermi energy. So the states around the Fermi energy may be more important than states far away from Fermi energy. And it has been known for a long time that Van Hove singularity leads to logarithmic divergent density of state in 2 dimensions, and a lot of interesting theoretical results about correlated electron phenomena near the Van Hove singularity. We generalized this Van Hove singularity to high order ones, and here instead of having 2 Fermi surfaces touch each other with a finite angle of intersection, at this high order Van Hove singularity, you see that 2 Fermi surfaces touch each other tangentially, or we can have more than 2 Fermi surfaces intersect at the same point. And these high order Van Hove singularities requires tuning some parameters, and we think that this might explain why these correlated electron phenomena are only seen near the magic angle, for example. So these high order Van Hove singularities, they have a stronger divergence in density of state, a power law divergence density of state, and that fits well with the STM experiments. And also, for example, a feature of this high order Van Hove singularity shown here is that the density of state is asymmetric with respect to the center of the peak, and you can clearly see that the asymmetry is present at the magic angle. But the same paper also showed the Van Hove peak away from magic angle, and there the peak is essentially symmetric. So all these suggest that these Van Hove singularities might play some role in the physics of these twisted parallel graphene. And so what I'm going to do, right, is that I'm going to take a somewhat impressionist point of view. This is a very biased opinion. I'm going to think of use this moiré systems as an excuse to study physics of these high order Van Hove singularities in a more general setting, right? So this reminds me of this painting from ancient China, and you see all these water waves, and to me that looks similar to this moiré. Okay, I'm going to take this this philosophy. Okay. Okay. So on the theory side, the reason I think that these Van Hove singularities and these high order Van Hove singularities are interesting is that they represent metals without any length scale, without any intrinsic length scale. So what I mean is the following: if you take a normal metal right? It has a characteristic scale, which is the Fermi wavelength, Kf. And you know, in a system with an intrinsic length scale, it cannot really be, strictly speaking, a critical, right? You know, we know the critical phenomena has no intrinsic length scales. Now, there's one class of metals which has no intrinsic scale, and these are sand metals, such as the Dirac point in graphene. There, you know, the Fermi surface is really a point, and this leads to a lot of work on this critical phenomena type of behavior in Dirac sand metals. Now, in 2 dimensions, with the linear dispersion, the density state actually vanishes. So it turned out that Coulomb interaction is marginally irrelevant. Leads to the long distance behavior of graphene seems to flow to the non-interacting limit. Now, if you have a system where the Fermi energy is right at the van Hove singularity, there's of course a full Fermi surface in the full Brillouin zone, but the divergence of the density state, right, which is what governs the thermodynamic property at low temperature, all come from the vicinity of these van Hove points. And if we look at the dispersion, the Fermi surface, just in the vicinity of these van Hove points, we again get a scale-invariant Fermi surface. So for ordinary van Hove singularity, the dispersion near the saddle point is just kx squared minus ky squared. So the constant energy contours are just 2 straight lines. Right? For these high-order van Hove singularity, this is what the contour looks like. There are 2 parabolic curves that touch each other. Again, there's no characteristic length scales. Right? So this allows us to take a continuum limit. Right? Just like when we talk about graphene, right? There is an underlying Brillouin zone, underlying lattice. But if we write down just the low energy theory, it has this linear dispersion that we can extend the momentum to infinity. Similarly, in the systems with these supermetals, if we just look at the dispersion in the vicinity of these saddle points, and then we can take the momentum, range of momentum to infinity, we get a theory without any length scales. Right? So this reminds us again of the critical phenomenon. Right? So that these supermetals in some sense critical. So now I'm going to study basically the effect of electron interactions in this kind of a supermetal. And again, now we're going to look at a different system. So remember that in twisted barrier graphene, the van Hove singularity occurs away from time reversal point, so they come in pairs, k and minus k. So it's more complicated. There are multiple high-order van Hove singularities related by time reversal symmetry right at Fermi energy. So here, instead, we study a simpler model which only has a single high-order saddle points at Fermi level. And to be concrete, let's consider a tie binding model, a single band tie binding model on a square lattice. But now let's make the hopping in the x and y direction to be inequivalent. And we also add a second neighbor hopping in the y direction. And the detail of this dispersion doesn't matter. You can add any terms you like. All I want to say is that whatever dispersion you choose, by tuning one parameter, you can get a high order saddle points right at this zone boundary at momentum pi 0. Okay? And at this high order saddle points, the 2 Fermi surfaces touch parabolically, tangential to each other. And if you look at the density state, it has this divergence with exponent e to the minus a quarter. Right? So there's a van Hove singularity at the y point. These are high order van Hove singularity. There's another ordinary van Hove singularity at the x point. Okay. So, and this model might actually be relevant to, for example, strontium loosening. And there's now a lot of physical focus of van Hove singularity in this material. And by applying uniaxial strain, one can actually move the van Hove singularity to Fermi energy, but only one of the 2 van Hove singularities at, for example, 0 pi. And this is the density state plot from the calculations. And you see that there's a strong density state divergence coming from the Fermi surface in the presence of strain. And this divergence is very close to the power law divergence at the high order van Hove singularity. Okay, so then this brings us to the question: what happens to these supermetals at low temperature in the presence of electron interactions? So we know that without interaction, as we change the chemical potential, there is a topological transition of the Fermi surface. The system changes from hole type to electron type. And now the question is, what happens when interaction effect is present? What happens at low temperature? So there are various possibilities. Broadly speaking, two types. The first is that the system might be unstable to symmetry breaking. And for example, ferromagnetism, or pneumaticity, superconductivity, or density wave. And this scenario has been widely explored in the context of ordinary van Hove singularity in cuprates, in ruthenides, in single-layer graphene, as well as more recently in twisted bilayer graphene. And also there is a very nice work by Claudia Chamon studying a model of high-order van Hove singularity, multiple high-order van Hove singularities with multiple types of interactions. And again, generically in that case, the system becomes unstable to certain symmetry breaking. So I'm going to now focus on a different scenario that these supermetal may remain metallic down to 0 temperature. Okay, and it turns out this is a case for a single high-order van Hove singularity in the range of interactions. So, so first, let's look at the mean field phase diagram for this situation of a single high-order van Hove singularity, right at Fermi energy. Or we're going to more generally, we're going to look at the phase diagram as a function of chemical potential and the interaction strength. And so what is plotted here is the density of the system of ground state and the magnetization of the ground state, spin polarization of the ground state that's obtained from a mean field calculation. And as you see that, for example, for a given finite interaction strength as a function of increasing chemical potential, the system always becomes ferromagnetic, okay, in a range of chemical potential when the Fermi energy is close to the high order van Hove singularity. Now this transition to ferromagnetism is actually first order. And at the same time, with this ferromagnetic transition, there's also a discontinuous change of the electron density. Okay, so this is consistent with the fact that these high-order van Hove singularities are right on the verge of ferromagnetism because it has a divergent spin susceptibility. It's also on the verge of becoming charge ordered because it also has a divergent charge compressibility. Right. So when interactions are present, for mean field calculation, there's a first order transition to ferromagnetism and to charge separation as a function of chemical potential. And this discontinuous change in magnetization and in carrier density, in electron density, become weaker and weaker as the interaction strength gets smaller. Okay. Now, when the interaction strength approaches 0, this region of ferromagnetic region shrinks to a single point. Right? And this is because when you have a divergent density state, in mean field calculation, infinitesimal interaction will be able to give ferromagnetism. Right? But the region of ferromagnetism also becomes vanishingly small. Okay. Is any questions? It's clear. So so now what we're interested in is how is this mean field calculation going to change when we take fluctuations into account? Right. This is very much like critical phenomena. Right. So in the critical phenomena, what we tune is, for example, temperature. In the presence of and we look at, for example, how the system changes from disorder state, a paramagnet to a ferromagnet as we lower the temperature, right? And in the absence of interactions, this transition is exactly described by just the mean field theory. But in the presence of interaction, in the presence of this nonlinear terms, the nature of the transition may be modified, right? So here there's this exact analogous. The chemical potential is the analog of the temperature in the phi-4 theory, while the interaction is the analog of the phi-4 term in the phi-4 theory. So So then let's now to study these effective fluctuations. We now look at this full theory, which has a high order by Hove singularity. The dispersion is quadratic in one direction, is quadratic in the other direction, and mu is chemopotential. And now let's add a contact interaction, right? It's point interaction between spin up and spin down electrons. So we're going to treat this as a quantum field theory, right? And analyze its behavior using renormalization group method. So and again, it's possible to use this renormalization group method because the Fermi surface is actually scale invariant. Right? There's no intrinsic scales, so this gives us a chance that the system may flow to an actual quantum critical point. And right, so this is really this theory is really a fermionic analog of phi-4 theory. Right? So there's a quadratic term and there's a quadratic term. And we know that in the absence of interactions, this chemopotential mu is relevant perturbation. We trap the system into either electron Fermi liquid or hole Fermi liquid. And now the question is, what about interactions? So one way to control the RG flow is to introduce a small parameter. In Wilson Fisher theory, for phi-4 theory, we use a dimensional as a parameter, the so-called dimensional expansion. So we can do the same thing here. So the dispersion is quadratic. The problem we are originally interested in is a two-dimensional system where the dispersion is quadratic in one direction, quadratic in the other direction. And this leads to a density state divergence, which is with exponent a quarter. Now we can extend the problem, generalize the problem. For example, there are D1 directions in which the dispersion has exponent n1, n is integer. And there are D2 directions in which the dispersion has exponent n2. And this gives a density state divergence with an exponent which is given by this. Right? So 1 minus D1 divided by n1 minus D2 divided by n2. So imagine that instead of having one direction where the interaction is quadratic, imagine there are two directions in which the exponent, the energy dispersion is quadratic. Then this epsilon becomes 0. Right? So this allows us to play this trick of dimensional expansion, that in treating this D2 as 2 minus epsilon, we can control the density state exponent. And we will see that this density state exponent plays a role of a small parameter that controls the RG flow. So, then what we do is we again follow the spirit of the Wilson RG. We impose an energy shell in momentum space, and we progressively integrate out modes that lie at the edge of this energy shell. Right? We thinning degrees of freedom, and we change variables, and we try to bring the action back to self. And in the process of doing that, the parameters in the theory would have been changed, and this allows us to keep track of the RG flow. And at the tree level, this is the theory is completely a quadratic theory. The high energy degrees of freedom and low energy degrees of freedom are completely separate, uncoupled. So in order to bring the cutoff back, we have to rescale momentum in this way so that the frequency, we change, perform a change of variable so that the cutoff goes back to self, and this imposes these transformations on the frequency, momentum, and the fermion fields, and it also changes the coupling constant G. So the consequence of this is just that the contact interaction is relevant, but any high order interactions containing any derivatives are irrelevant. Right? So when epsilon is small, only the contact interaction is relevant. And this makes sense, right? Because we know, for example, if the density state has a logarithmic divergence, then the contact interaction is actually marginal. Right? So when the density state is barely power law diverging, only the contact interaction is relevant. And so again, this is very similar to the structure of the Wilson-Fisher theory for phi-4 theory. Right? In the phi-4 theory, below the upper critical dimension, the phi-4 term is relevant. Right? So then we go to the one loop level. in the one loop level, the interaction is going to be receive corrections from two processes. One is a particle-Hove process, and the other is a particle-particle process. Right? So this particle-Hove process, if we do an RPA treatment, is what gives rise to ferromagnetism. And the particle-particle process is what leads to screening. Right? So in the presence of repulsive interactions, this screening tends to reduce the interaction strength. And when we look at this problem in the RG approach, we see that we're going to need to include these two diagrams into account. And again, I want to mention that in general, the allowed interactions of this form, there's a 4 fermion term, and 1, 2, 3, 4 really labels the frequency and the momentum of these on the incoming legs. But again, we can expand this interaction function in powers of the momentum, and only the zeroth order term is relevant. Okay, this is another way of saying that we only need to think about the contact interaction, because any additional interactions are irrelevant or at the tree level already. Okay, so when we look at these two diagrams, it turns out that the particle diagrams gives a zero contribution when the external momentum and frequency are set to be 0. And what this means is that at 0 temperature, there's really no particle screening from states near the energy shell, lambda. Right? So on the other hand, the particle-particle contribution process is present, and it tends to decrease the repulsive interaction. So the upshot of this is that if you look at the RG flow of the coupling constant, at the tree level, it's relevant, but then there, at one loop level, there's a G² term with a negative coefficient. Okay. Another effect of the interaction is that it actually shifts the chemical potential. Again, this is structure of these two equations are very similar to 5-4 theory. Right. So again, chemical potential plays a role of temperature in 5-4 theory, and the Gaussian fixed point corresponds to the non-interacting supermetal, while the Wilson-Fisher fixed point corresponds to interacting supermetal. And you clearly see that from this RG flow, there is a fixed point, right, at finite interaction strength. And we would like to understand the properties at this interacting fixed point. And for that purpose, we need to compute all these susceptibilities at this interacting fixed point. And these susceptibilities are governed by the scaling dimension of relevant operators. And these are the various relevant perturbations. Mu is the chemical potential, H is the external field, and the delta is the external pairing field, right? And so if we look at the response to a chemical potential, this tells us about the charge susceptibility. Okay, the scaling dimension of mu determines the charge susceptibility. The scaling dimension of H, external field, determines the spin susceptibility. And turn out that to one loop level, they diverge with exponent epsilon, which is a non-interacting densive state exponent. So at the one loop level, the interaction at the interacting fixed point, these exponents are unchanged. However, if we look at the pairing susceptibility, okay, when we compute the scaling dimension of the pairing field, it actually acquires correction due to the interactions, and the pairing susceptibility actually is non-divergent. Okay, so this delta operator is actually irrelevant at the interacting fixed point. So this is very different from the non-interacting case, right? In the non-interacting fixed point, the external magnetic field, the Zeeman field and the pairing field all have the same scaling dimension because the spin susceptibility and the pairing susceptibility all diverge as a densive state. Okay, but here at the interacting fixed point, the pairing susceptibility is totally different from the spin susceptibility, right? So this already tells us that this interacting fixed point is not a Fermi liquid. One can actually,
Intuitive description of why that happens?
Yeah, this actually is not quite surprising. So in a sense, even for a system with a finite Fermi surface, the pairing susceptibility, in the presence of interactions, the pairing susceptibility does not have a log divergence anymore. They become finite.
Because they're repulsive.
They're repulsive interaction, exactly. Yeah.
Now, what about the long-range part of the Coulomb?
Right. So I'm also.
Are you going to get to that? Or?
No, I'm not. Yeah.
So you don't know what.
So I assume that there are other parts of the Fermi surface which already screen the long-range Coulomb interaction. Yes. That's right.
But you can't treat that systematically.
Not yet. Right. Okay. So right. So right from this one loop calculation, we can already see that the system is not a Fermi liquid. Now the gold criterion for deciding whether it's a Fermi liquid or not is to look at the quasi-particle weight, right, which corresponds to the scaling dimension of the fermion fields. This actually requires a two-loop calculation. It's something I didn't appreciate before. If you same way, if you look at 5-4 theory, right? If you look at all the textbooks, like the Chigging-Lubansky textbook, the textbook will tell you everything about all the critical exponents except the anomalous dimension of the fields, of the boson fields phi. And the textbook always said that this requires beyond the one-loop calculation. So here we have a similar situation that we can get the susceptibility of all these relevant operators, right? Susceptibility from the scaling dimension relevant operators. But if we are right at the critical point, right, the only exponent left right at critical point is the correlation function of the fermion fields, right? And that defines the anomalous dimension. So this requires a two-loop calculation, and Hiroki, really did this heroic work. At least to me, looks heroic. And the thing is that with two-loop calculation, it cannot be done. Really, it cannot be done in any straightforward way in the Wilson RG approach. So one has to use this field theory RG. So anyway, so Hiroki developed that scheme for our problem, and it showed that the fermion fields indeed has an anomalous dimension at the two-loop level, and it's proportional to the critical interaction strength squared. So the interaction strength at the fixed point is a moderate epsilon. I should mention that because of this structure, right, this epsilon here. At the interacting fixed point, the G is a moderate epsilon, so this anomalous dimension of the fermion fields is a moderate epsilon squared. Okay, so this tells us that the quasi-particle weight actually really vanishes. So basically, so what we get is that when we use this renormalization group approach, this quantum field theory approach, we show that basically if we have a scale-invariant Fermi surface with a power law divergent tensor state, with local contact interactions, it leads to a non-Fermi liquid state, a non-Fermi liquid fixed point. And our analysis is fully controlled in the same way that the Wilson-Fisher fixed point is controlled. There's a small dimensionless parameter which is related to the density state exponent epsilon. And even in the original problem we are interested in, epsilon is a quarter, so it's already quite small. Also, I want to make a comment that scale invariance really plays a crucial role here for an ordinary non-metal which has a characteristic Kf. Very often at low temperature, instability occurs. For example, the most famous one is this Condensed mechanism, and that is related to this 2Kf non-identicity of the susceptibility. But if you have a situation where the Kf is absent, there's no characteristic scales, then this Condensed mechanism does not apply. Right? So this is exactly what happens in our situation. The Fermi surface has no characteristic, has no intrinsic scales. And also, other approaches to non-Fermi liquid, it requires some singular interactions, for example, mediated by gapless bosonic excitations, etc., while here, right, we're really starting from a fermion system with just local interactions. And it's not because interactions are particularly singular, but because the density state is singular that leads to this non-Fermi liquid state. So now we can put everything together to look at the whole phase diagram, right? So as a function of the chemical potential and the function of interaction strength, so this is a mean field phase diagram. There is when interactions is weak, there is an electron Fermi liquid, Hove Fermi liquid, separated by a small region of ferromagnetism, right? However, when we take the fluctuation into account, this mean field phase diagram is going to be modified in this region, right? This is the region where the interaction strength is small, chemical potential is very close to the Van Hove singularity, right? So instead, what we have is that that there is a line over which, instead of becoming ferromagnetic, the system remains metallic. This is a supermetal state, interacting supermetal state, and only above a critical interaction strength, the system becomes ferromagnetic. So there is a fixed point along this line, which is this fixed point.
So that means you're saying there's a second phase transition up higher.
There's a second phase transition that's higher. Yeah.
Do you have any way of treating that system?
Not really. We have some thought. We have to form. I think it cannot be treated by just using the fermion. Maybe one has to formulate the problem as fermion coupled to some order parameter field. Yeah. So yeah. I cannot. Yeah, that's a good question. Yeah. So also one can take an even broader view. In addition to these two parameters, G and mu, remember that to obtain the high order Van Hove singularity in the first place, we have to tune the dispersion, right? The more generic case is that in the system, we have an ordinary Van Hove singularity. Only when you tune some parameters, such as the twist angle, you can turn a ordinary Van Hove singularity into a high order Van Hove singularity. And if you go past this, the system will, a high order Van Hove singularity splits into two ordinary Van Hove singularity again. Right? So this kind of changing of the dispersion is represented by additional parameter lambda. Right. So in this overall phase diagram, what really happens is that this supermetal state, right, interacting fixed point, is really a multi-critical point. One needs to tune two parameters to reach it. One has to tune the chemical potential to the right place, and one needs to tune the lambda, right, the changing the dispersion to the right place. Right. So in the presence of interactions, these original non-interacting dispersion can be modified. Right. RG can generate additional terms to the non-interacting dispersion. But the key point is that by adjusting one tuning parameter lambda, one can always reach this fixed point. Okay. So it's a multi-critical point that requires tuning two parameters. One is the chemical potential, which is controlled by the carrier density, by the gate voltage in the moiré materials. And the other is a knob that changes the dispersion. But only we need to tune one such tuning parameter, we can reach this high order saddle points. So and that I think is an advantage of these moiré materials that we can always use gating to bring the chemical potential to desired fitting, and on top of that one can play with electric field, etc. to tune the system. Okay. So this is basically the end of the first part of this talk. Any questions? So I want to make a yes.
So you mentioned this is the case for only one high order Van Hove singularity.
Right. Exactly. Yeah.
What happens when you have multiple of them?
Right. That's excellent. So right. So I was just about to make that remark that all this is for the case of a single high order Van Hove. When there are more than one Van Hove singularity right at Fermi energy, which is the case for twisted biaxial graphene, and it seems that generically the system actually would flow to a symmetry breaking state. So instead of remaining metallic down to zero temperature, some kind of order sets in. And again, a very nice work is by Claudia Chamon, dealing with the high order Van Hove singularity. And we also look at the case, for example, of ordinary Van Hove singularity when there are multiple of them. Again, when there's interactions between different Van Hove points, the system seems to flow to a symmetry breaking state, such as a density wave or superconductivity. So this example that I've just shown, as far as I know, is the only example where the Van Hove points can lead to a non-Fermi liquid down to zero temperature. Yeah. So, right. Ask some questions. Yeah. Okay. All right. So let's see now. Move on to the next part. So how much time do I have?
You have until 10:45.
Okay. I may end a bit early. So okay. All right. So now let's talk about this another. So far, I've been taking a weak coupling approach, right? So in this Van Hove scenario, that for example, when interaction is weak, right, we get an interacting fixed point. This interaction strength measured in the units of cutoff is of order epsilon. Epsilon is the density state exponent, right? So all this physics happens in a sense at weak coupling. Now what happens when we look at strong coupling limit, right? So in reality, these moiré materials are probably intermediate coupling when the interaction strength is comparable to the bandwidth. That's the most difficult regime. So seriously, we can explore the weak coupling limit and explore the strong coupling limit, and hope they can tell us something useful, and hope we can extrapolate between the two limits. Now in the strong coupling limit, the natural one natural starting point is to start with the Hubbard model, right? This is a paradigmatic approach to strong correlations, and it turned out for twisted bilayer graphene, right, that a Hubbard model has very interesting features, and we will probably hear more about this in the afternoon. And here, all I want to say is that we look at the twisted bilayer graphene with this particular lattice structure, and we found that this system is actually described by a Hubbard model on the honeycomb lattice, where the sites of the honeycomb are the ABBA regions. Now, if you look at the STM experiment, for example, shown at the beginning, all these regions of high tunneling density state are in the AA region, which form a triangle lattice, right? So the density state are concentrated in the AA region, and yet from the analysis of the band symmetries, we infer that the linear center has to be on the honeycomb site. So to reconcile these two conclusions, what happens is that when we explicitly construct the linear function in this work with Cauchino, it turned out that the linear center is at the ABBA region, but each linear function consists of three pieces, right? Has three peaks, right, which are actually centered in the AA region. This is AB, this is AA. Right. So it's a very interesting feature, and these three pieces of the linear function, they have a relative phase. They have phase winding relative to each other. Anyway, so the punchline is that for twisted bilayer graphene, a Hubbard model description is, let's say, twisted. Twisted is sophisticated. On the other hand, for all these other moiré systems, like trilayer graphene on HBN, for twisted transition metal dichalcogenides over a wide parameter range, these are really described by simple Hubbard models on the triangle lattice. Okay, so in these systems, there's analogous AA stacking region, and the linear orbitals are centered in these triangular lattice sites. So this allows us to construct in a straightforward way a Hubbard model on the triangle lattice. Now, one generic feature in these systems is that unlike the Hubbard model for cuprids, there are two orbitals involved here, and these two orbitals really come from the presence of two values, right? Remember that in graphene, right, there are these two values, and when you form a superlattice, when you form a moiré, these two values remain essentially decoupled at the single particle level. So that's why the low energy degrees of freedom comes from both values, and these two values are represented by the two orbitals in this Hubbard model. So in particular, let's focus on this ABC trilayer graphene on HBN that you heard from Feng Wang yesterday. And this system consists of three ingredients, right? The first is that there is a trilayer graphene, and that provides us with these low energy electrons. And if you remember that trilayer graphene, the low energy dispersion has a cubic dispersion, right at the K points. And a second ingredient is that electric field, which is again is not, which can tune the bandwidth, and it not only tunes the bandwidth but also modifies the dispersion of the moiré band, which again is what can give rise to these high order van Hove singularity, etc. And the final ingredient is this boron nitride substrate. And because of the lattice mismatch, this boron nitride provides a moiré superlattice potential. So essentially what we're dealing with is electrons in twisted bilayer graphene moving under the presence of a periodic potential, okay, from the HBN. And so this type of band structure has been solved, calculated in this Feng-Wan's paper. And you can see that there is a narrow band, right, narrow band here. And as you heard yesterday, that as a function of the carrier density and in a certain range of the electric field, you see that there's an insulating state when this moiré band is partially filled. At 1/2 filling and a 1/4 filling, insulating states both appear. And we think that this half filling state can be understood already from the recoupling approach because of these high order van Hove singularity. On the other hand, for the 1/4 filling, there's nothing special onto the Fermi surface. So to understand the physics as this 1/4 filling insulating state, we have to turn to the strong coupling approach. So this is the rest of this talk is about this 1/4 filling state in this trilayer graphene. So again, if we take the type binding model, the one-layer functions are centered in the AA stacking region, and they form a triangle lattice. And there are two orbitals coming from the two valleys, and the system has a 3-4 rotation symmetry, time reversal symmetry, which interchange the two valleys, and reflection symmetry. So, so in this triangle lattice, we can introduce the nearest neighbor hopping, second nearest neighbor hopping, and these are the dominant hoppings. One thing to notice is that because the electrons in each valley is not time reversal invariant, right? Time reversal symmetry interchange the two valleys. So within a valley, there's no time reversal invariance. So this means that when electrons of a given valley hop on the triangle lattice, it can pick up flux. Right? The hopping can generically be complex, right? Very much like the Hove model. And indeed, based on symmetry, the first neighbor hopping is allowed to be complex, but the second neighbor hopping turns out has to be real due to a reflection symmetry. I'm not going into the details. So we end up with a 2-orbital Hubbard model on the triangle lattice with complex hopping T1 and real hopping T2. It turns out these two hoppings are the largest, so we can neglect the rest. And for the interactions, we use the simplest on-site Hubbard interaction, right? That give an energy penalty for deviation from having one electron. Right? It only depends on the total number of electrons per site. And so with constant inch rate, who is here, we studied the physics of this Hubbard model, 2-orbital Hubbard model with complex hopping on the triangle lattice. So I'm now going straight to the strong coupling limit. At the 1/4 filling, there's this Hubbard interaction U guarantees that there's only one electron per site. Then there's a virtual processes of electron hopping between nearest neighbor sites, second neighbor height sites, and that generates the spin orbital exchange interaction. Right? So by a T over U expansion, what's shown here are the two kinds of exchange processes. In the first type, we have electrons on two sites within the same valley. So this exchange process does not depend on any flux. Does not depend on the flux because electron hops forward and then backward, right? And the two processes have opposite phases, so they cancel each other. On the other hand, you can have electrons on different valleys, or different orbitals in this representation. And then, when the two electrons are exchanged, the phase factors, they do not cancel, but they add up, right? Because remember that the two valleys are the time reversal conjugate of each other, so they carry opposite flux. So in this case, the hopping picks up flux. So at the end of the day, this is the form of the exchange interaction. And let me explain what it is. At every site, there are 4 possible states. Right? Electron can be in valley plus or minus. It can be in spin up or spin down. Right? So these 4 states are labeled by this alpha or beta. and this T operator is just this exchange operator, right? It exchange state alpha to beta and vice versa. The nearest neighbor exchange interaction has a phase factor, right? And the second neighbor exchange interaction is real. Okay, so when the phase factor is 0, this exchange model Hamiltonian has a manifest SU4 symmetry, right? So in the absence of any valley flux, the valley and the spin, you can group them together into a 4-component degrees of freedom, and the exchange Hamiltonian is SU4 symmetric. But when the valley flux is non-zero, so valley and spin degrees of freedom are inequivalent. Right? There's a full spin rotation symmetry, but for the valleys, there's only a value U1 symmetry. So that's why the full symmetry in the presence of the valley flux is SU2 cross SU2 cross U1. So the two SU2s refers to spin rotation symmetry within each valley, and the U1 represents the valley number conservation. Right, so this is a full symmetry of this problem.
Is there an estimate of how big that flux is?
Yes, I'm not showing it here, but actually in the Noah can correct me if I'm wrong. So I think for this, the valley flux depends on the applied electric field, and for the we did some estimate for this particular electric field strength, the valley flux is of order pi over 2, I think. On the order pi of 2 is pretty large, yeah. And microscopically, this valley flux comes from this trigonal warping of this energy dispersion in trilagraphene. Right. So this is the way time-Russell symmetry is broken. Time-Russell symmetry, within each valley, if you have a K2 minus K symmetry, then there's no valley flux. But even in trilagraphene, there's already a trigonal warping. So within each valley, the dispersion is not K minus K symmetric. And this trigonal warping is actually amplified by HBN superlattice potential. Right. Now, on the other hand, it turns out for twisted TMD, the trigonal warping is much smaller, and this valley flux is very small. Yeah, so that's why for the twisted TMD, this SU4 symmetry model is a good starting point. Okay, so now with this exchange model in the strong coupling limit, one can study its ground state. We take the most mundane approach, right? This semi-classical ground state, assuming that the ground state is a product state, right? And we try to basically this V represents how the spin is polarized in spin and valley space at every site, and then we calculate its potential value using this product state. Now, what's interesting here, and this is really Constantine's work, is that interestingly, within this semi-classical approach, the ground state is the semi-classical, the energy, right, is completely minimized. Now, every bond energy is minimized when the ground state takes this pattern. Okay. So before I explain this pattern, I want to just make this point clear that if you take, for example, a spin 1/2 Heisenberg model on the square lattice, right? The semi-classical ground state is anti-Fermatnian state, right? Spin up on A sublattice, spin down on B sublattice. And in this ground state, the energy is minimized for every bond within this classical approach. But if you take a triangle lattice with a spin 1/2 electrons, the semi-classical ground state is this 120-degree state where electrons form this pattern, right? So in this case, the ground state energy for every bond, right, is not saturated, because the best situation is to put two electrons exactly opposite to each other for a given bond, right? But because of the frustration, right, that not all bonds can be satisfied at the same time. So that's why the compromise is that this 120-degree state is the semi-classical ground state. Here, we have a situation which is just like the Heisenberg model on the triangle lattice, right? So one might think this is actually a frustrated problem, that the ground state energy is not saturated every bond. But interestingly, because this is a 2-orbital Hubbard model, okay, there are 4 possible states to choose from. It's possible, and this is shown here, it turned out that the ground state energy is minimized at every bond. Okay, so it's actually a frustration-free problem. And to look at it more carefully, to explain this a little bit more. So if you look at this exchange model, exchange Hamiltonian, right? What it does is it wants to flip the states on sides I and side j, right? It exchanges the states on side I and j, and the interaction is j1, j2 are repulsive. So a ground state energy is within the semi-classical approach. The energy is minimized if on all neighboring sites and second neighbor sites the states are orthogonal to each other. So and this pattern satisfies that. If you pick up every site, look at all its nearest neighbors and second neighbors, you always encounter different states. Okay, so that's why it's a frustration-free state. And you see that in this state, we have a 4 sublattice order. The unit cell becomes 2 times 2, 4 times larger, and this is a density wave. Right? It's a spin density wave. It's also a valley density wave. Right? So the plus minus represent 2 valleys, and the arrows represent spins. So this is a particular ground state in the degenerate manifold. So the remaining states in the degenerate manifold can be obtained by rotating the spins of each valley, right? So we can separately rotate all the spins in the plus valley and the spins in the minus valley. Right? So and there's a manifold of these ground states. So this is a semi-classical state, and one can further analyze the effect of quantum fluctuations at 0 temperature, and this is basically the reduction of the order moments due to quantum fluctuations that's plotted here as a function of the ratio of J1, J2 over J1, right? So you see that when the J2 is above a certain threshold, which is 0.12 around, this density wave is stabilized against quantum fluctuations. While if the J2 is smaller than this value, within this analysis, we find that the order moments reduces to 0, so we get a disordered state. Okay. So so this is basically the main result from the analysis of this 2-orbital Hubbard model on the triangle lattice, and so this can be, I think, compared with experiments. For example, in this state, it's not spin polarized, it's not valley polarized, and this determines the behavior when we apply in-plane magnetic field or the out-of-plane magnetic field. In this system, the in-plane magnetic field couples to the spin, the out-of-plane magnetic field predominantly couples to the orbitals. So because this state is an antiferromagnetic type of state in spin space and in valley space, we do not expect any polarization. So in the presence of external field, the spins will cant, for example. So this can be compared with future experiments. So there are also many open questions. For example, what is the nature of this disorder phase? Right. So within the semi-classical approach, we are not able to determine the nature of this state. So it's an open question. And in this 2-orbital Hubbard model, what happens when we dope the system away from this insulating region? Does this give rise to superconductivity? And if does, what kind of superconducting state? All these are open questions. So, so with this, let me just summarize that basically, these are the 3 topics covered: the topology and the quantum geometry in 2D materials, and there the key player is this direct point. Right? When direct point opens up a gap, it leads to various topological states, and direct point also. Massive direct point also give rise to barrier curvature, and that can be probed that leads to Norm's Hall effect, nonlinear Hall effect. In the case of these moiré materials, the system at half filling, at quarter filling, always have a Fermi surface instead of a Fermi point. But interestingly, that when the Hove singularity is near the Fermi energy, one can look at the physics in the vicinity of these saddle points that allows us to formulate a problem in terms of field theory, and without any intrinsic scale, the system becomes a supermetal, which is at the border of ferromagnetism, charge order, and etc. So I like to think of the supermetal as a intermediate fixed point, right, that governs the behavior of the system in a wide temperature range. So as you lower the temperature, the non-interacting supermetal may become unstable. It may give rise to new states, symmetry breaking states, or the non-interacting supermetal can remain metallic down to 0 temperature, and that leads to a non-Fermi liquid, which we can address in a controlled way. I've briefly discussed that the strong coupling limit, where very much like the Hubbard model, but now because of the presence of 2 valleys, there exist 2 orbitals at least, and this multi-orbital leads to new physics. So, for example, even on a triangle lattice, we get a frustration-free ground state at quarter Philly. Okay, thank you.
We definitely have time for questions.
So in the multi-orbital Hubbard physics,
Right.
in your effective model,
Right.
it seems like we get a large degeneracy at the end of the day.
Correct. There's a degenerate ground state manifold, right?
Right.
At 0
So
temperature. Yeah.
do we can we live it by by considering higher order term and stuff?
Oh yeah, that's an excellent question. So, for example, there is a when we look at the interactions, here we are using the Hubbard interaction that only depends on the number of electrons, right? But one can further include the exchange interaction between the 2 valleys, right? The S dot S, and that exchange interaction would actually reduce this SU2 cross SU2 symmetry to just a single SU2, right? So when the exchange interaction is present, there's only global spin rotation symmetry, but there's no spin rotation symmetry within each valley. So this probably, although we haven't looked at it carefully, this probably would lock the orientation of spins of the plus values and minus values relative to each other. Yeah, so right, that's a good question. But the largest interaction in the system is the Hubbard interaction. Yeah, and actually that is a general comment I'm going to make. That because in these systems, in these moiré systems, the electron density is very low, right? So in the low density system, the Coulomb interaction is long range, right? So they are the strongest interaction. It's in the same way that when we analyze quantum Hall problems, right, at low density, the interaction, the dominant interaction we first consider is Coulomb interaction. So in my opinion, that in all these moiré materials, the leading order question is what is how do you handle Coulomb interaction? The Coulomb interaction may be screened by the metallic gates, but still they are much larger than the short-range interactions, right? That only is present when 2 electrons are very close to each other, right? Because on average, the electrons stay pretty far away from each other. So the largest interaction is Coulomb or screen Coulomb interaction. Yeah.
Even the framework of the interaction that you introduced with the Hubbard interaction, when you do the expansion, for example, there should be some term like something that is analogous to S dot S cross S, like because you have the flow through all this triangle.
Oh, you mean the 3 side?
Yeah.
Right, that's a good question. Yeah, you mean when T over U is not too small?
Yeah.
So one need to take into account 3-side exchange. Yeah, that's an excellent question. Yeah, that's right. I think that's right. Yeah.
Sure.
Yeah, it's a good point.
Have you considered that?
No, not yet. Not yet. Yeah. So this is really the strong coupling limit when we assume that T over U is very small. Yeah, that's a good question. Yeah.
In the supermetal
Right.
divergent
Right.
density of states, so the thermal power should be huge.
Right. Yeah. This is exactly what we are thinking about.
Asymmetric.
Exactly. Exactly. That's what we're thinking.
Do you know? Have you estimated how? In terms
No,
of K,
not yet.
how much?
Yeah, because usually thermal power depends on the disorder. I think to calculate thermal power. So that requires dealing with the presence of disorder. But I totally agree with you that this is
From the entropy density point of view. What
in some limit, I think that there's some formula for thermal power right? Without any external magnetic field, which is thermodynamic, purely reduces to thermodynamic quantities. But it's, I haven't. Yeah, we can discuss it. Yeah, but this is an excellent point that the usual van Hove singularity is symmetric, E minus E symmetric. So if your Fermi energy is right there, right, then there's no thermal power. But in this case, we have a divergent dense state, but it's also asymmetric, right, which is already seen in the STM STM data, right? If you just look at them. Right, if you just look at this, right, with your eye, you can see that, right, the peak is asymmetric with respect to its center. Yeah. So, so you should have interesting thermal power. Yeah. Yes.
Can I go to the frustration rate?
Sure. Yeah.
So in that one, if we look at one of the spin in a random valley,
right.
So 4 of the spins around it are just anti-parallel, and 2 of them are parallel.
Right.
So will this induce any distortion for this triangular?
Yeah, actually that's right. So if you take this ground state, right, you can see that, for example, the rotation symmetry is broken.
Yeah.
If you look at the plus values, right, and the minus values, they form alternating stripes, right. So the rotation symmetry is broken, so it should couple to the string.
Yeah, then it's not a perfect triangular
Correct.
in 2 of the directions.
Yeah. So in other words, this ground state breaks the 3-4 rotation symmetry. Yeah.
But if every bond is in its ground state, they all have the same energy, so it wouldn't distort necessarily.
So I think the
Right? It would only distort if it was frustrated, right? That some of the bonds were frustrated, right?
yeah, I think the way to reconcile these is that if we take additional exchange interaction between the values into account,
Yeah.
then the
it
ground
will
state will distort. Yeah,
Right.
yeah.
Your basic
Yeah.
model, it
Right.
won't distort.
Right.
You know, because if it's really
Right,
frustration
right,
free,
right,
it
right,
won't
right. Every
distort.
bond is happy.
Happy.
Okay, that's a good point. Yes, yes. Once we take the exchange interaction into account, then you can see that, for example, this direction and these other directions are not equivalent. Yes, thank you. Thank you.
I had another question,
yes.
which is, yesterday Fan Wang was talking about valley ferromagnets, and
Right.
I actually forget which
Right, that's an
which
excellent point.
moiré material
right. So,
that
yeah,
was, and
yes,
how
yes.
does that fit with this? It's
Yes,
different,
yes, excellent,
obviously.
excellent. Yeah. So in this system, the behavior is really depends on the electric field. So as Fan Wang said, there are 2 regimes where electric field in plus direction and minus direction.
Okay.
And the churn insulator, which comes from presumably comes from the validation number of the within each valley, that only occurs under one direction of electric field, while everything I'm talking about here today is the other direction.
So this is in the case where there's
No churn number.
No churn.
Yeah.
And when you have
Right.
a churn number,
Right.
you need a different number.
Completely
model.
different. And then, in fact, if there's a churn number, that it's impossible to construct a
Oh,
single
you can't
band.
make the 1-year orbital.
Yeah, I cannot make a single band.
And that's where he had the valley ferromagnet.
Exactly.
Okay.
And actually, one way.
So it's the same material, just a different.
Same material. So this is a very fascinating system.
Yeah.
So
Okay.
now, one way to sort of intuitively to think about 2 different regimes is the following. If you have this, we can see here. Yeah. So this trilayer graphene has 3 layers, right? And HBN is, let's say, coupled to the top layer. And then when you apply electric field, you can pull electrons in trilayer graphene either towards HBN or away from HBN. So when it's towards HBN, then that's the regime where it's no churn number, because electrons strongly feel the presence of the HBN potential. So they just got stuck into these AA regions. While if the electric field push the electron away from that interface, that amazingly leads to the valley churn number. Yeah. Although, as Feng said yesterday, there's also a very good discussion. I didn't realize before that there's a still question that the churn number, observed churn number is 2, while the valley churn number from single particle calculation is 3. So the origin is still, I think, somewhat open. Yeah.
Okay, with that, join me in thanking Professor Fu for his stimulating lectures this week.